Hello everyone, my name is Jesilia Sraj and I'm going to be taking you through this presentation. Our project is basically about real-time 3D avatar translation of Ugandan Sign Language using large vision models and blender rigging. So basically, that's what we are going to be working upon through our final year project. To begin with, our project goal is basically to come up with a system that converts Ugandan Sign Language to an animated 3D real-time and then basically we are going to use computer vision and graphics. To begin with, in the previous lecture, we are tasked to find out about 3D and 2D and why we are going to choose 3D over 2D for our sign language translation using computer vision and advanced graphics. To begin with, some of the sign language, basically like the American Sign Language and the British Sign Language, plus also our Ugandan Sign Language, are not just hand shapes. They basically are complete linguistic systems, like they use part of grammar. For example, the hand shape, the orientation, the location, the manual markers, and the depths and proximity. These like the facial expressions, these can't be captured using 2D, the mouth, the way the mouth moves, even the body. Some of them can't be captured using 2D. So the reasons why we are choosing 3D over 2D is basically, reason number one is resolving the ambiguity, or in science, this is basically 2D. In 2D and 3D, they are a bit different. So in 2D, let's say in sign language, please and sorry have the same gesture or the same way of putting it out. So in 2D, please can be interpreted still the same as sorry. So basically 3D can get those gestures, and 3D, basically the position of the hand, and then differentiates between please and sorry. Another one is handling occultation and viewpoint invariation. So basically in 2D, the hand blocks the other. So let's say the hand blocks the other, or the hands block the face. So it cannot interpret well. But in 3D model, especially when it's trained well on 3D data, it can differentiate when the hand, depending on the depth between the hand and the face, basically interpreting the sign language properly. Than the 2D, when you block the face, it can't interpret very well. Then the other thing is accurate representation and movement of movement. So basically 2D basically uses XY, and 3D uses XY and Z trajectory in tracking these movements. So let's say when you're pulling, when you're coming closer, 2D cannot analyze that, but 3D can analyze it. Then the other thing is about the camera perspective. In 2D, when you tilt the camera, let's say at 45 degrees, it will interpret it in another way than in 3D. In 2D, it's like a flat surface. When you tilt the camera, the sign language will also change, or the positions of the hand will change. But in 3D, the trajectory of X, Y, and Z can also be can also work to help us overcome that for the camera perspective. To begin with, we are tasked to come up with the papers and read about the papers, basically depending on our project. So the first paper I was able to research about and read about is continuous sign language recognition through transformers and media pipe landmarks. Basically, that's the abstract of the paper. So basically, the problem statement in this paper is that these sign languages are complex linguistic systems distinct from verbal languages. Okay, basically these ones rely on visual and gesture clues and facial body movements. Basically these sign languages, that's what they depend on, than our other languages like us who talk, even just signs, visual signs. So in this paper, while interpreting these signs, it's harder for some signs, let's say due to blur. So the transition vary also in speed, flow, and execution between individuals. So basically, they wanted to solve that problem of blur transitions and also the speed and the flow while these people are trying to execute these sign languages. So the project goal was to create a real-time recognition method for translating sign languages into verbal languages, our language. So the aim for this was to make it easily accessible and to use in modern language translation. Okay, to create a system that is easy like to interpret these sign languages. So basically the key advancements they used. So basically the key advancements, like how they did their project, is that they were using AI, modern AI, for sign languages. So they already use the existing products or the existing AIs or the existing models to create their solution. So they use deep learning and computer vision basically, and MediaPipe does feature extractions, like extracts the landmarks from the video and offers it to a corresponding site. So basically the key reasons for that is like to reduce computational load and also the real-time cross-platform on all cross-platforms, like on deployment. So basically they didn't start from scratch. They wanted to create something that is smooth and easy to use. So they didn't want to use every model or develop their models because it will be heavy. The input size will be heavy while training, and so they just fine-tune the existing models. So that's the transformer model, and here it was used to help in processing the sequences of landmarks and transforming into glosses. Glosses are like the signs. Let's say someone has done a sign, so that gloss it represents a word in sign. So these glosses are the ones that are going to be interpreted by the GPT-4 mini, which they used, and they fine-tuned it to transform these glosses into verbal language. So when after getting the signs, they're turned into glosses, and these glosses are the ones that are understood by the GPT, and then it gives you the output. So basically, their methodology, so it's just a three-stage real-time translation pipeline. So basically, they record a video of someone signing, let's say someone signing, then MediaPipe does the extraction of hand landmarks and then converts them into sequences of futures, and these futures are then transformed by the transformer into glosses, and these glosses map to signs. Basically, that. Then the translation is just done by the GPT, which reads these glosses and then turns them into the words of the verbal language. Then the output is just a message or an audio of that sign. Basically that. And basically they were emphasizing using it on all platforms like mobile devices. So basically it was just a smooth workflow. So their architecture was, as I told you, like they have a camera inputs the video. This video is taken as frames. These frames are the ones that are fed into the MediaPipe. MediaPipe basically reads this video and then gets the landmarks. These landmarks are the ones that are passed through the transformer. The transformer also goes into details, has the encoder and then the decoder. I'll be showing you that. So this transformer gets these landmarks and then transforms them into glosses. I told you glosses are signs that represent someone. So these glosses are already understood, can be understood by the GPT, and then the GPT is the one that does the translation of those glosses into words. So it can be text. So here they use the tool for text to speech. So this one can be like Google text to speech. So it transforms text into audio, basically that. So when you dive deep into their methodology, if you go in context, the same as what I was explaining before. So the signer communicates in sign language, gets the video, and this video, MediaPipe does feature extraction, basically XYZ coordinates, those are the landmarks. And those landmarks then are the ones that are converted into glosses using the transformer. This transformer, basically, it includes two models. If you go details into the paper for classification. One, they used first an offline model and then the real-time model, basically to get those glosses. So the output gets the glosses. So these glosses are the ones that are fine-tuned by the ones that pass through the fine-tuned GPT-4 that provides you with the sentence, and then you get the message of that sign. So this is the representation of the transformer that transforms the signs. So basically, this is the landmark. The landmarks then transformed into the coordinates X, Y, Z. These are the coordinates, and then they are passed through the encoder. The encoder, there is some architecture there that after encoding them, they are transformed into the decoder. The decoder is the one that outputs can output probabilities of, because it has to convert them into glosses. So outputs those glosses, and then they're the ones that are transferred into the GPT-4. Basically that. So another paper I searched about is a joint model for video and language representation. So basically this was for Google. They fine-tuned some big model BAT into a video BAT. So basically this is the abstract form. So their challenge was like for this paper. Basically the challenge is that most of these models, or most of the AI models, learn using labeled data, and the challenge is labeled data is so crucial for deep learning but hard to acquire. You can't go on, let's say you want to, for us going to do the Ugandan Sign Language, you can't go on like making videos with their annotations, or that it's tiresome. But so they come up with a solution for self-supervised learning, which is vital for unlabeled data. So the limitations of the existing AI models that use self-supervised approaches is that they focus on low-level features like textures and short temporal scales. So their goal was to achieve to discover high-level semantic features corresponding to actions and events unfolding over long-time scales. Like some features, let's say, already exist in some videos. So when a model keeps on learning different videos and sees the gestures, all the features in that video, it can be able to predict that this video, this person was doing this and this, other than training, giving it a video with the annotations of what it is doing. So the video watches, the model watches a lot of videos, and then it analyzes them, all the videos. When you give it a video, it can just remember the gestures in different videos which were even of unlabeled data. So what is VideoBAT? VideoBAT just is a joint visual linguistic model designed to learn high-level features without expecting supervision. So its foundation, as I told you, is BAT model, and this BAT model is the bigger model. So they came up with the VideoBAT for analyzing video to text. So the core idea is that it learns by directional joint distributions over sequences of visuals and linguistic tokens. So it's like gets this video and then turns it into tokens, and these tokens are then the ones that are turned into text. And also it gets text and then turns it into tokens, and these tokens can also output a video. Basically that. So the key components that they were using the automatic speech recognition system. This one converts speech into text. When someone even is about to speak, this one can convert that text into speech. So the vector quantization. So this one just it's a pre-trained. It's delivered from a pre-trained video classification model. So basically, it helps in creating the words, the visual words or the visual tokens. So these visual tokens are like the ones that are going to be turned into a video. So the BAT model for it just helps them. Since I told you it is fine-tuned from the BAT model, the BAT model just for learning these joins, all the sequences in the tokens, and then creates for you a video. So basically, the BAT model is for learning joint distributions over sequences of discrete tokens. So the BAT model learns this token and then can be able to output a video, or learns the visual text and then outputs the video. So modeling, so learns the model in form of XY, where X is the sequence of visual words, and then Y is the sequence of spoken tokens. Basically that. So the video BAT architecture, for it transforms raw. How they did their pre-processing, their architecture is that they did some minimal changes to the BAT, since I told you that it was merged from the BAT. So this transforms the raw visual data into discrete sequence of tokens to leverage pre-trained models. So the BAT just transforms this visual data into discrete tokens. Then the visual tokenization for it, like it gets the sample, let's say the sample of the video you have input. It creates frames of like one and a half seconds of videos. So it learns like that from the video. Let's say you have input a video of 10 minutes, so it's going to be cutting it into or chopping it into 1.30 seconds, 1.5 seconds, and then it learns from the features in the clips. So BAT is the backbone, like the one that the larger model consists of those layers, as you can see. So their goal was to come up with, to learn the high level features without explicitly supervision. So basically they just give the model a lot of unlabeled video, so it just learns depending on the different features within the video. So the core idea, as I talked about, is the BAT, and then they converted it and then they made the video BAT, and which helps to transform the raw visual data into discrete sequences of visual words to that pre-trained model, and then scale it using the BAT implementations, something like that. So basically, that's what it combines in their architecture. So maybe to explain about the visual tokenization. So visual tokenization is like, I was using video, so it transforms these pixels to visual words. So it converts raw visual data into discrete sequences of visual words to be capable with BAT. So then I talked about changing the whole video into frames of 1.5 seconds, and then yeah, that's how the video BAT, that's what about is all about tokenization. So the steps they used after feeding in the videos or the frame, it does that, changes that video, let's say 10 minutes into 1.5 seconds, making many clips, and then they do the feature extraction, basically to get out the vectors from each frame or in each clip, and then using a pre-trained S3D. So Basically, to continue with another paper I reviewed, basically, another paper was about proposing hand gesture recognition system using media pipe holistic and LSTM. So basically, that's the abstract. So basically, the overview of this paper. This paper proposes a method for recognizing and tracking human hand gestures. So basically, they were trying to solve some problem. Basically, in some applications like the virtual reality, medical monitoring, and smart device control systems that use them. So basically uses media pipe algorithm for gesture tracking and long-term, short-term memory for classification. So basically they were focusing on some specific gestures like punching, cutting, swiping, like the way they do while controlling, let's say virtual reality, while playing games, the way they use those gestures. Then basically they were focusing more on the upper body skeleton and their corresponding gesture levels. They are not focusing on the whole body, they are focusing on the upper skeleton to extract these gestures. So the problem is that most of the computers or the methods we use while we are interacting with these computers is that we use mouse and keyboards to feed in the information, and also voice and pointing, let's say, also motion sensors. Basically, that's what we use while we are inputting data into the computer. So the challenges with this is that when you try to use the voice control, you can't use it in a noisy background or in a noisy place. So it's difficult to capture the signal, what you are trying to input into a computer due to noise. Then the motion sensors, let's say some rings they use, the upper ring can control some things. So these motion sensors are expensive. The technology of motion sensors are expensive. Even the traditional gesture recognition systems that are available require high data, quality data, and also specific lighting. And they use extensive processing, and which makes it not easy. And also another challenge is deep learning models like YOLO can be heavy with performance dependent on training on high quality data. That these models are heavy, that are trained to do that are heavy and highly require good data to train. So another one is the existing pose estimation algorithms like open pose can be slow while trying to recognize some, on some hardware they can be slow. So basically they needed this solution to be efficient in their games and also smart homes and then medical monitoring. So basically they want to use the technology in that while eliminating the other challenges. So basically this is the architecture within their paper. Basically the proposed system was built, as I told you, for virtual reality to get these gestures. So as you can see in the diagram, there is data input. Let's say you input a gesture, so the media pipe extracts the skeleton, focuses on your body, and then extracts the skeleton, maps something like a skeleton, and then tracking by media pipe, the one that puts dots on that skeleton, and then it sends it to the LSTM, which does the feature extraction, and then the classifying, and then you get the output. So basically, to explain more of the architecture, you input data. Basically, it's going to be a sequence of frames of video containing images of the upper body and arms, and then you're going to extract the skeleton by using media pipe. So media pipe detects the body and extracts the key points within the body based on the hand, these key points, the joints, all of them, and then tracking by media pipe holistic tracks the body, and then frame by frame, and then it includes the face, posture, and everything, and then provides the key points on the body based on the eyes. Goes on putting key points on each point of the body, and then feature extraction is done by LSTM. So it gets this extracted skeleton from the body, and then it has an LSTM network which extracts important features, and then still does the classifying by LSTM. So based on the learning of the features on the skeleton, which was input, so it classifies these gestures and then gives you the outputs from the human skeleton, and then the corresponding gestures performed by the video. So that's, as I was discussing, the key components they used were media pipe holistic and then the long-term short-term network. So basically in the media pipe holistic there were some details or more they used, which was the bed pose and then the palm. So to continue with the methodology, the way they did the skeleton extraction and tracking using media pipe holistic. So the purpose is to detect and extract the human skeleton from videos. So it gets your video and extracts that skeleton with coordinates, and then the media pipe holistic for it tracks this and then integrates the multiple models for the body, let's say hand, face, and then sends it to this blade. So to continue with the blade pose model. So blade pose model basically estimates the human posture, like the half of it. So it gets the image and then detects the pose and then aligns that pose and then tracks the pose. Basically it does that, as you can see its architecture here. So they also use the blade face force, and this one they ignored it because it was expensive, and basically they were focusing on hand gestures and then the body. So they ignored the blade face model while implementing their solution. Another methodology is getting the gesture extractions and classification. So to continue with gesture extraction and classification, so basically they were using the LSTM. So the purpose was to learn the extracted skeleton features and classify gesture labels. So this LSTM, after the media pipe extracting the skeleton and the skeletal features, it learns the labels on it. So basically what is LSTM? LSTM is long short-term memory, a special form of RAM capable of learning long-term dependencies. So basically it was designed to overcome the long-term dependence problem, and for it helps in remembering information for an extended periods of time without training. So this long-term short-term memory remembers the information of the video that is sent to you without going back to learn through it. So it is suitable for video data and processes the entire data sequences with help of to differentiate between easily confused statistic and then dynamic features. So it helps in differentiating different poses or gestures. Let's say when you're static and when you're dynamic, like when you're swiping the hand right or left. So it helps in differentiating all these sequences, all these data sequences. So basically you input into LSTM. So videos, let's say cut videos of 30 frames and media pipe. So basically here they used videos. These videos were put through media pipe. Media pipe extracts the skeleton, and these skeletons values are the ones that are passed through the LSTM. So basically that's what it is. So the data set they use for training, they used OpenCV library, and basically they were collecting videos, like 30 videos of 9 gestures, and then train their model. So basically we are focusing on gestures like punching, swiping, basically those gestures that are used in games to play games. Yeah, that brings me to the end of my presentation. Thank you.